Okay, in this tutorial we're going to go through the process of laying out a CMOS inverter in the Sky130 process using Magic, and we're going to then create a hierarchical layout involving a cascade of two of those inverter cells to make a CMOS buffer. But maybe the first thing we should do is take a look at some documentation on the PDK. So this is at read the docs IO Sky130 nanometer. So the URL is skywater-pdk.readthedocs.io, and this is very much under construction, and there are a bunch of stuff over here on the left that look very promising, like analog design with Magic, and it's all to do. And so there's a lot of stuff here that's still in process. But if we go up to design rules and we look at, let's see, layer definitions, looking for the stack diagram, process stack diagram. Okay, so this picture shows shows the vertical stack up of all the different layers in the technology. So down here we have the P substrate, which is where the N channel transistors live. The N-well, which is the local substrate where the P-channel transistors live. We've got diffusion. There could also be diffusion in the substrate. Then we've got the polysilicon gate, which is over a thin oxide. We have polysilicon that's not over top of thin oxide, which is called field poly. And then there's the first level of metal, which is a local interconnect layer. We use this for routing, making local connections inside a cell and maybe connecting locally from one cell to another. And then we have our layers of metal. We got 5 layers of metal and a contact layer between each successive layer of metal. So contact between metal 1 and the local interconnect is called MCON. Then above metal 1, the connection layers are called vias, and the connection between metal 1 and metal 2 is called via 1. I think it's also just via in Magic. And then via 2, via 3, via 4. I don't believe we have access to the cap2M and the cap1M layers, which are basically extra layers for making a nice metal insulator metal capacitor. So I think when we go to make capacitors, we're probably going to have to pick a couple of layers, like maybe field poly and local interconnect or something like that, or maybe local interconnect in metal 1 or something like that, for making our capacitors, but I'll have to check into that and get back to you. So these are the different layers that we're going to be drawing with, and these are how they're related to each other. If you want to make a connection from, like, let's say metal 3 down to diffusion, you actually have to connect through all of the intermediate layers and stack up all the contacts on top of each other. And so if you can stay closer to the surface of the silicon, you're better off doing that with your making your connections. I think when you're routing cells, you should try to stick with polysilicon and local interconnect for all of your local connections within a cell, and then maybe you have to go up to metal 1, but I would not go much above metal 1 in routing your cells. That way all the other metal layers are available for flying over top of the cells or making power distributions and stuff like that. Okay, so anyway, that's the read the docs. I guess over here in this, basically there's stuff down to the PDK contents, and below that pretty much everything else is still under construction. Maybe we can actually contribute to the whole thing ourselves once we figure some stuff out this semester. Yeah, we'll see about that. Okay, so the first thing I'm going to do is I'm going to go into my documents and then inverter tutorial directory that we've been working with here, and I'm going to make a new directory for the layout. And I'm going to start Magic from here, just so when I go to save my cells and find them, I'm in the right directory. Okay, so when we run Magic, we get 2 windows popping up, and I'm going to make this one a little bit bigger. And I still want to have this one down here kind of I want to be able to see what's in it because there's some useful information that's going to be displayed in it. So we're going to maybe do that. So now you'll see here we have a box, okay, and the way that we typically work in Magic is that that box defines an area, and we can paint some layer inside this box, and we can select stuff inside the box, and we can copy stuff inside the box. And so I can use the left mouse button to define the lower left-hand corner of the box, and then I can use the right mouse button to define the upper right-hand corner of the box. It's probably actually useful to have a 3-button mouse to do layout with Magic. But you'll notice here, when I make my box, if I hit the B key, or I type :box, those are the same thing, I get some useful information about the box down here in this window in the lower left-hand corner of the screen here. It tells me the dimensions of the box in microns, and in lambda, which is kind of an internal scalable unit, and then the internal Magic grid. And it also tells me the area in all those units over here on the right-hand side, and that's very useful information. So one thing to note right away is that if I make the box 1 by 1 grids here, in microns, that's 0.01 microns by 0.01 microns. And so that's a really fine grid, and that's not going to be a very useful grid to draw layout on. And so I played around with a bunch of stuff, and given our minimum channel length is 150 microns, I found that making the grid 50 nanometers is much better. And so the way that we can change that and change the grid snapping is go :grid, not GERD, grid, 0.05 microns, 0.05 microns. That defines the grid spacing, the user grid spacing for X and Y dimensions. And now I also turn the grid lines on. Okay, so I'm going to turn the grid lines off by going :grid again. And now I'm going to change snapping by going :snap user. So I'm going to change to the user grid for snapping. And now you can see that my grid is, there's my smallest box, 1 grid unit by 1 grid unit, and it's 0.05 microns. Okay, so that's going to be much more useful for counting off, three times the 0.05 gives us a minimum length transistor and minimum width poly and that kind of stuff. So that's going to be a much more useful grid to work with. Now the other thing is there's different sets of design rules that can be enabled at a given time, and I'll explain a little bit later why that's useful. But for drawing a cell, we'd like to enable the full design rule set. So I'm going to go :drc style, drc paren full end paren. So this turns on checking all design rules. And until you get used to the design rules and while you're doing a small cell layout, it's best to have all the design rules enabled. Magic does something called incremental design rule checking, which is really, really great. It'll show us design rule violations as we draw a layout interactively, and then when the design rule violations disappear, the little white dots that appear to show a design rule violation also disappear. That's really, really, really handy. But you can imagine that for a very complicated layout, maybe when we're looking at the whole chip or something like that, having it check all of the design rules on all of the geometry that's present could slow things down quite a lot. And so they have reduced design rule sets that can be enabled that, for instance, if we're doing routing, we might not want to check all the design rule violations or check for design rule violations on all the geometry that's not changing. We just want to check for design rule violations on the metal layers or something like that. So there's a design rule style that's for routing and so on. So that will make things go faster. But for us right now, enabling the full design rule set is going to be what we want to do. And so now I'm going to zoom out. So Shift Z zooms out, Z zooms in, and Control Z zooms to the box. Okay, those are very useful commands to note. The arrow keys do panning. And so what I want to do is I want to make a box that's maybe the size of the transistors that I'm going to use, which are the same size as the default size in the schematic symbols in Xscheme. And so that was 0.15 microns by 1 micron. So now my box is 0.15 by 0.55. And now it's 0.15 by 1.05. Now it's the right size. And so I'm going to paint poly in here. And I can do that by going :paint poly. And now my box is filled with poly. There are other ways that you can accomplish that. So if I move my box over, and then I middle click, point the cursor at something that has poly already there, and I middle clicked, it paints the box with whatever's under the cursor when I middle click. And so I can do that from other geometry that I've previously drawn, or I can do that from over here in the layer palette. So if I find the right layer, I think this is polysilicon. If I middle click over here, I get the same thing. You'll notice these white dots here. That is the design rule violations. And so if I draw my box around the area that has the design rule violations, I can go :drcy, and it will tell me, oh, this is poly spacing less than 0.21 microns. And so these two pieces of polysilicon are too close together. Okay, so I want to get rid of this poly because it's not useful for what I want to do here. And so I can do that a couple of different ways. I could click on the middle mouse button out here to paint empty space in there, which will erase the poly. Or if I were to put poly back in there and I go :erase poly, it would erase the poly that's in the box. Okay. So now I'm going to draw some N diffusion, and in order to do that, I want to have, I want 10. So that would be here. So if I go paint N diff, I get N diffusion. And I need 10 there. And I'm going to paint N diffusion over my poly, and that will turn the poly into N-tran. So you can see this hatched region in here is actually N-transistor, where the poly crosses the N diffusion is where my transistor is. Okay, so the first thing I'm going to do is I'm going to extend the poly out by 3. You have to extend the poly outside of the beyond the end of the transistor by 3. And you can see that these design rule violations up here went away. I can do that down here as well. But you can also see that I have a bunch of design rule violations in this whole area. And so if I ask it why it's upset, it says N diffusion distance to P tap, which is a P substrate contact, must be less than 15 microns. So I haven't drawn any P substrate contacts. It wants to ensure that I've got at least a P substrate contact within 15 microns of this transistor. And so I'm going to draw the contacts to the N diffusion here before I start drawing the N diffusion, or rather the P substrate contacts. So the N diffusion contacts are what we're going to work on next. So that's going to be :paint Li for local interconnect. And then my actual contact is going to be 4 wide, and it's got to be 3 in from there. So I'm going to paint, and it's N diffusion contact, NDC. Okay, so there's my N diffusion contact and my local interconnect that's on top. And so now I'm going to copy this box over here, and I'm going to copy this box here, and I'm going to middle click to paint my contacts. So there are my contacts, and I'm going to make a merged substrate contact over here. So I'm going to go paint, and it's going to be P substrate diffusion, PSD. And now I'm going to extend the local interconnect over to there. I'm going to make my P substrate contact PSC. Now you can see those white dots that were over top of my N diffusion have gone away because now I have a P-tap, or a P-substrate contact, here defining the potential of the substrate. Okay, so there's my N-channel transistor. And now I would like to make my P-channel transistor. And the easiest way to do that is going to use the geometry I've already drawn. So if I hit the S key, that will select, off to the side here, that will select the entire cell. And that would make the box coincident with the entire cell. If I go :select area, it selects all of the geometry inside the box. And I can copy that to the north, so in a certain direction by a certain distance. It's the compass direction, so north. Say I want to do that by 30. Now I have a copy of my N-channel transistor that is above my other one, and I'd like to turn it into a P-channel transistor. And in Magic, there's an easy way to do that. So if I paint N well over top of an N-channel transistor, Magic will automatically flip the sense of the diffusions and the substrate diffusions and whatnot to make it into a P-channel transistor. So if I go paint N well, it turns it into a P-channel transistor. Now there's some design rule violations because I need to overlap or extend the well by at least 4 outside of all of my stuff, the P diffusion and the N substrate diffusion. So now I have removed some of these design rule violations, but you can see that I'm still a little too close here between my P transistor, or my N transistor, and the N well. And so I'm going to select area again, and I'm going to move, so :move, just like I could copy, I can move north 1. And I can then use the dot key to repeat that. I can use the U key to undo. And so I moved it up so that the little white dots went away, and now I am just far enough so that I don't get design rule violations. So now I have my N-channel transistor and my P-channel transistor, but to make my inverter I need to connect the gates up. So I'm going to draw a little bit more poly to connect those pieces of poly up to each other. And I'm going to connect the drains together with local interconnect. And the minimum width for local interconnect is 4. And now I'm going to come down here, and I'm going to make the output go off to the right here, to the edge of the well. And I'm going to make the input come in on local interconnect, and then make a poly contact down here, so that when I instance one of these cells next to another one, I will automatically connect the output of the first cell to the input of the next cell. Okay? So I'm going to make my poly contact, and the minimum size I can make the polysilicon for a poly contact is going to be 8, and so 8 by 8, and right there. If I paint poly, I'm going to paint local interconnect, and now my poly contact is going to be 4 by 4. Paint PC for poly contact. And now I want to route this in on local interconnect. See, I want this to be, that looks about right. And extend the box out to here, paint LI. And now I want to extend this LI region down here, and then off to the right-hand edge of the cell. Okay, that's my input and output connection. Now I'm going to route the power across here in metal 1, and VDD across here in metal 1 as well. So again, I'm going to make these out to the well edge so that I can just, by abutting these two cells next to each other, the power supply connections will automatically connect to each other and feed through. So there is the box that I need for my metal 1. So I paint M1, and I'll move the box up here to paint my VDD rail. It'll click on that metal 1 to give me metal 1 for the VDD. And now I've got to make my local connection down to the local interconnect layer. And that's going to be paint mcon metal contact Okay, so that is all of the geometry for our inverter. And a couple things here. If I hover the cursor over my piece of local interconnect here and I hit the S key once, it selects a box on that layer. And then if I hit it a second time, it selects a little bit more of something that's electrically connected to that. And if I hit it a third time, it selects everything that is connected electrically to that piece of geometry that I started on. And so that's a very useful feature. That's called flashing a net or flashing a node. And we sometimes use that to check for VDD to ground shorts and things like that. So I can do that with the output here, and you'll see if I hit S key 3 times, it lights up the source and drain diffusions of the P channel and N channel transistors. If I select the ground rail, the substrate plug shows up here, as well as the N diffusion for the N channel MOSFET source. If I do the same thing on VDD, it lights up even the well. Okay, so the last thing I'm going to do is I'm going to put some labels in here to define the input, the output, and the power and the ground rail, and I'm going to make them ports, which will facilitate making our hierarchical schematic. So to make a label, or to make a port, we're going to start out by making a label. So I'm going to zoom in by hitting Control Z. I'm going to make my input port here by making a 0 width and height box. So you left click and right click on the same spot, and you get that little plus sign there. And we can make a label by going :label, and then the name of the label, I'm going to call it A, like we did for the schematic symbol. And then the direction we would like the label to appear relative to that little plus sign, which is going to be the west. And that should create our label. Now, unfortunately, the font is very, very small by default, and that probably is relative to the very small grid size, very, very fine grid size. Now, there is a set label command which allows us to change the parameter of the fonts that are used for the label, and I haven't quite got my head around to how that all works yet, so that's still something I'll have to figure out. But for our purposes, this will be fine. And if I want to make that label into a port, we can do the :port make and then give it an index. So it's going to be the first port. And so now that little yellow A has turned into a blue A, indicating that it is a port. Okay. We're going to do the same thing for the output. We're going to move that over here. And we're going to do :label Y east. And so we can't see it at this level of magnification. If I zoom in and then move over, you can see there's a Y there. And if I go :port make 2, it turns it blue, indicating that it's going to be a port. I'm going to make the VP port first for the third port. And now here is a situation where we have both metal 1 and well underneath the cursor, and so we can specify what layer we would like to attach the label and hence the port to by telling the label command which layer to attach it to. So if we go :label, we're going to call this VP for the positive power supply connection, west, and we're going to say that this is on M1. And then we go :port make 3. And we're going to come down here and do the same thing. So colon label VN West, and then port make 4. Okay, so that is our inverter. Control Z, and we need to save this. So let us go colon save inverter. Inverter. Okay, so now we've named the cell inverter, and we are in business. Except, looks like my local interconnect layer here is not quite long enough. Oops. So let me port remove, erase label, and let's extend that by 1, and let's make my label again. Colon label Y east, colon port make 2. Okay, so it looks good. All right, that looks good. Okay, so let's go up here, cell new, and let's make a buffer. Okay, so now we're editing buffer. Okay, we still have our good grid. Now I'm going to do colon get cell inverter, and now we have an inverter cell, or an instance of our inverter cell, which is called inverter 0. And it's currently, the contents of it are hidden, and we can hit the X key by putting the cursor over the hidden cell, and that reveals the contents of the layout underneath the cell. If I hit the Shift X key, it hides it again. Okay, so I can show it, and I can then conveniently just move the box over. If I want to get another copy, I can go colon get cell inverter, and that will instance a second inverter. And if I hit the X key, you can see the second inverter, and you'll notice how the metal 1 ground rail here connection just goes straight through. And if I hit the S key over top of the metal 1, you can see that it selects everything, including the substrate contact and source diffusion for the N-channel transistor inside the second inverter. And if I hit, let's say I'll start over here on the local interconnect layer for the output of the first inverter, it'll select the gate, the gates of the transistors in the second inverter. Okay, so it knows how to go down inside the cells in making the sort of flashing the intermediate node there, which is super cool. And so now we're almost done with our buffer. The last thing I'm going to do is I'm going to put some labels at this level of the hierarchy. And in order to do that, what I like to do is I like to paint a little bit in the layer that I'm going to make the port label on. Paint LI here for the input, and then for the output label, and do the same thing. And then I'm going to make some metal 1 for the VDD connection and ground connection. Like so. So if I hide Shift X and select this cell and Shift X, you can see if I hide those, I've got geometry on the metal 1 and the local interconnect layer here kind of over top of the geometry that's inside the subcells. And that just gives me a little piece of geometry to attach the labels to at this level, the hierarchy. All right, so I'm going to zoom in here. And I'm not going to actually make these ports at this level because I don't want the buffer cell to be wrapped inside a subcircuit wrapper. But you could, if you made these ports and you extracted a SPICE netlist from this layout with ports at the top level, it would make it a subcircuit, and that's probably what you would want to do if you wanted to simulate the layout. If you want to do layout versus schematic, I think it's better to not make them labels at the top level, okay, or not make them ports at the top level. So we're going to create a label. I'm going to call it A West. And then we're going to make the output of the whole thing. We call it Y. East. And then we're going to go over here. Let's do this one first. Label VP West, and we're going to put this in metal 1. Okay. So select the whole thing. Control Z to zoom out to the selection, and that's our buffer. I'm going to save that, and now I'm going to extract a SPICE netlist from this cell just to see what that looks like. And in order to do that, we have to extract all, extract all. And what extract all does is it basically finds all the NMOS and PMOS transistors and all of the diodes and capacitors and resistors. And if we wanted to, we could extract parasitic elements in our circuit representation that would represent like the parasitics of the interconnects and things like that. And then we run a command called X to SPICE to turn that extraction into a SPICE netlist. Okay, but there are a couple of settings we have to change. The first is we want to make it a hierarchical netlist, and so we're going to do :X to SPICE hierarchy on, and we want to do X to SPICE scale off. So that has to do with the physical dimensions of the width and lengths of the transistors and how they're written out to the SPICE netlist. And so we want the scale parameter or model card to be off. And so we can then run X to SPICE. And hopefully, if I go back out here and pull up a new terminal window, yes, there's buffer.spice, and if I do gvim buffer.spice, we can take a look and see what we got. Okay, so here we have our inverter subcircuit, okay, with 2 transistors in it, an NFET and a PFET of the right type, an NFET 01V8, and we have the order of the ports, or the order that we specified, right? So A was the first, Y was the second, VP was the third, and VN was the fourth. And for a MOSFET in a SPICE deck, the order of the terminals is drain, gate, source, bulk. Right? So here we have the drain is the Y, which is output. A is the gate, which is the input. and then the source and bulk for the NMOS transistor, or the negative power supply. And for the P-channel transistor, it's the positive power supply. So that's good. The width of the transistor is 1e plus 6 micro. So it's 1,000,000 micros. So that's going to be 1 micron. It's kind of screwy, but that's apparently the way they had to do it. And so the length is 150,000 times 10 to the minus 6 micro, and that's going to be 0.15 microns, or 150 nanometers. Okay, so that's good. And then at the top level, we have two inverter instances. The A input, or the A node label, was what we call the buffer input overall, so that goes into the input of the inverter, the first inverter, and then we have this intermediate net name that we didn't pick, but it picked for us, which is the A port of inverter 1. So the input of inverter 1 is the intermediate node. And so that makes sense as the input to the inverter 1. The output of inverter 0 is connected to the input of inverter 1. And so that all looks good. Okay, so in the next segment, we're going to look at how to use that netlist, and a netlist that we can write out from Xscheme to do layout versus schematic comparison for verification purposes. Okay, but that's it for this tutorial. Thanks for watching.